J, then we can have some charges, for example here, -2 and +2 on the other side of the face pointing to the eye normal, okay, so that we can write that your whatever charge is dependent through the dielectric constant by your input forces like this. We can review also that circuit as a capacitor, okay, and the properties of this capacitor are related to some geometrical properties, the thickness and the surface to which are collected all the charges, okay, so that we can say that those charges I are given you by C and the voltage, okay, then you put the things together and you can say that the output tension that could be measured on your end circuit are given you by this E, J, H, or what are they, electric, A2, and then MX times twice. Okay, remember that your capacitor, the capacity of a capacitor is the dielectric times A2 over H. But that is not good, because in order to have the persistence of this voltage, you have all the charges be there, but they are not there, as we already discussed. So we have to consider your overall equivalent circuit that is composed by a part that is related to the piezoelectric itself. So we have RQ and CQ that are the capacity and the resistance of the piezoelectric component. Then we have to consider the resistance and the capacity on the connected cable. And finally, what we got is the amplifier stage with its own resistance and capacitor, M, measuring device, and Cn. And that is equivalent to a sort of circuit with a RT and CT, okay. So the output is dependent on what's happening to the input, that is your initial value divided by tau. Tau is a time constant, RT and CT. Okay, so just 2 words about that. The overall frequency transfer that was asked by you. Okay, the overall frequency representation is a convolution of what we call the electrical part as a function of the frequency times in the frequency domain by the mechanical part. And that is also dependent on the frequency. So what we can say is that the overall transfer function is composed by, in the frequency domain, so Hg over F, is composed by 3 regions, okay, like that, in which we are having a first part that is the attenuation, and we have a sort of constant part, and then we have an R. Remember, we refer to the F1, that is the cutting frequency of order of hertz. Then we have the F2, that is the 3 dB, or some kilohertz. And then we have the natural frequency of the mechanical device, that is greater than the previous one. Okay. And that ends your self-assessment test. Okay.
Scusi, una domanda.
Prego.
Ma quella è una convoluzione in frequenza e quindi un prodotto in tempo, oppure era una convoluzione in
No.
tempo che è un prodotto in frequenza?
Convoluzione nel tempo prodotto in frequenza.
Ok, perfetto, grazie.
So that is a time convolution that leads to a product in the frequency domain, this HD. Okay, do you have any special questions? So just to remark you, we have attenuation here. Then we have working region there. And then finally, distortion area. Okay, so we would love to have to operate at lower frequencies than F1 and the higher frequencies than F2. Okay, and of course, this is about 1. Okay, questions?
Professore, scusi, avrei una domanda sulla seconda domanda, ma non c'era anche una parte, diciamo, sulle questioni delle condizioni al contorno? Quindi mi
Sì,
sembra che
sì.
lei alla lezione avesse detto che si passava da una condizione isostatica a una iperstatica.
Va bene.
Potrebbe spiegarlo, per favore?
Of course, I'm just trying to synthesize all the questions, but however, what we can say is that by making a remark of the question number 2 concerning the boundary condition, okay, what we can say is that it is preferable to have, let's say, the whole aircraft now and then having very nice plot of the whole aircraft like that, okay, something like this, okay, and that is a scale 1 test in order to reduce as much as possible all the effects of the boundary condition. We have to introduce a 6 degree of freedom spring, okay, so that everything is retained, okay, and then supported by this load. And why that? If you consider whatever structure under isostatic conditions, of course, there is no effect in the loading path when measuring whatever quantities. If we are having an hyperstatic structure, then there is a strong influence of the location of your measuring transducer, because it does alter the loading path, and therefore all your measuring could be not representative of your actual conditions. Okay, so what we are doing is, in general, try to support the overall structure, so scale 1 structure, so that also effects on the boundary condition to the connection, for example, the connection between the one wing and the fuselage or whatever subsystems are are the ones that we have to consider. So there is no simplification in representing the junction, representing the different interaction between components. And while supporting the overall structure like that, what we are having is that in the neighborhood of this 6 degree of freedom spring, there could be some interferences, but when you are referring to other points far from them, then what we are having is the right behavior of your structure. Okay, so we are, in this case, by using this such a device that is a single degree of freedom spring system, we are supporting the structure. Thus, when referring to an aircraft, we are referring to the flying condition because it's a self-sustaining structure. All the boundary conditions, the true boundary conditions, are there. Remember the connection between wings and fuselage. Okay, the effect of the supporting device is very local, so we try not to introduce that in your measuring chain, and therefore you are having a quite good representative representative measurement, yes, of the actual reality that this could be the defined aircraft. Okay. Okay. Is that okay for you? Any other questions? Now, if there are not any other questions, let's see a different point. And as I told you before, let's recall some tools that are very useful when dealing with the structural dynamics. And these are some statistical tools. So let's have some recalls. On statistical. Statistical tools. Okay, let's try to introduce these statistical tools topic by recalling what is the probability of an event A. I know that you have some suggestions about that, but the probability of an event A is defined, let me say, a priori. It is without actual experiments. Okay. As the ratio that I think you can should be familiar with that. So the probability P relative to the event A is defined as the ratio of the, let's say, number of outcomes favorable to the event A, okay, with respect to the total number of possible outcomes. Okay, and this ratio could be defined also as NA, the number of outcomes that are favorable to A, divided by the number of possible outcomes that could be N. Okay, by the way, this number of possible outcomes could be also the number of samples. Okay, so the total number of samples that we can have for a specific test, for example. Now, having said that, and of course, this is a priori because we are not taking any experiment at all. We are just predicting what could be the probability, okay, of such an event. Now, let's assume that we are available a number of samples that is very, very large, okay, compared to what we can evaluate, compare with our actual number of outcomes, okay. So what we can say is that when this number of possible, the total number of possible outcomes is going to a very large value, then our probability could be regarded as a function of the for event A as the limit, okay, of NA over N. Okay, just to focus on this, let's assume that we are having a specific test. Okay, then we are here. We are having a picture plot in which we have the number of samples. Okay, that we are having, and here are the number of samples that are in favor of some events. For example, that we have here 10, that we have 20. So here we are, for example, 1, 2, 3, 4, 3, and then we have just one over here. And that is what we are considering as the ratio between the number of outcomes favorable to a possible event A with respect to the number of outputs. Okay, in our analysis, what we can add, this is not a point here, sorry, just to be sure that we are not mistaking anything. Okay, so what we are having is that 3 events when we are having 10 as your event label, and 1 event that is in favor of event label 20. Okay, when we are moving to an infinite number of samples, that picture could be redrawn as this one. Here, once again, we have the PDX, and then we have X, and then here we have 10, and here we have just 1. Okay, so here we have 3/4, and then we have 1/4. As you can see, we are moving, when lots of data are available, from a discrete distribution to a continuous distribution. And because it is continuous, we can also derive its derivative, okay, that is called PGF, that is the derivative of your probability of an event A with respect to a change of this event A. And this PDF is the acronym of the probability density function. Okay, from its definition, we are having that if we are evaluating the probability density function in all possible combination, in all the possible domain, what we are having is the integral of the PDF of the event A, okay, with all the possible A, of course, is equal to 1. Okay, or if we are considering that function, okay, the PDF function of A having sort of distribution like this, for example, then what we are having is the value of this area, that is the integral, for example, here, okay, is the overall area is representative of the probability that your event, okay, is happening between A and A plus A, okay, being this the value of A, and this is CA. Okay. Now, when referring to outcomes that are that depends on just one parameter, okay, then we can rewrite something more detailed in that. So referring to outcomes X that depend on just one parameter, that is your X dependable parameter T, for example. When we write this equation, this definition, sorry, the Px of T, okay, we are saying that we are referring to the probability density function. Please note I'm using the lower p instead of the capital P, okay? And this PDF is the PDF, the probability density function of a specific event X evaluated, okay, when the parameter is having the value T, okay? And when referring to the probability density function between two events, for example, x1, t1, and x2, t2, okay, then we are referring to the probability density function relative to outcomes, okay, that are in the domain x1, t1, and x2, t2. That is, we are selecting a specific range of variation of your whatever variable. Please note that when we are starting our discussion referring to the probability, okay, of an event A, we are having a discrete number, okay? So for a given A, we have that probability. There is no link between one A and the other one, okay? Discrete value. But if we are evaluating that A with a very large number of values, that is, we are going to have a limit, evaluation of the limit of that ratio, then we move from a discrete distribution to a continuous one. We can derive, because of this, derivative function of this probability that is called the probability density function. This probability density function has some important properties that we just saw before. And now we are adding one more constraint, or better, one more characterization of your whatever outcome. Now, what we are saying is that your whatever outcome is in turn depending on one parameter, and this parameter is called T. And therefore, when we are viewing this probability density function having two dependencies, the meaning of this lower p is that we are referring to a probability density function for a specific event X that is evaluated at a parameter value T, okay? And thus, when we are referring to a range, therefore we have two couples of parameters, X1, T1, and X2, T2. Could you please tell me what is for you the definition of a random phenomena, or what is a random phenomenon? It's a question for you.
There's no particular method. It's just done kind of, I want to use the word randomly.
Yeah, that is just, let's say, one part of definition. You are just saying that a random phenomena could be viewed as if I have a sort of a number of experiments, the outcome of this experiment is whatever. That's right?
Yeah.
Okay, but that is just one part. You are missing the best part, if you want.
How you get to the solution is done randomly.
No, the random phenomena is the first part, what you said. The second part is that there is a sort of underlying pattern, okay, that is characterizing that phenomena. For example, time, for example, T, whatever, okay? So it is not completely basic, but there is something that is driving your random outcomes, okay? So we can try to write that as that if we are having repeated experiments or whatever test, okay, that are yielding different outcomes, and that is what we are already discussed, the first part, but they are having a certain underlying patterns about them. Okay. So your random phenomena, when we are referring better to random phenomena, we are referring to some outcomes that are not related one with the other one, okay, but there is something, okay, underlying those patterns that are characterizing your whatever phenomena, okay? So basic numbers are completely basic. There is no phenomena underlying those numbers, okay? But random phenomena, there is something beneath that is telling you what would be your output. Well, although it is basic, but we are having an underlying pattern, okay? Now, second question. Stochastic process. Do you have an idea of what is it? It's a question. Do you have an idea? All of you went through aerodynamics, so I know that
I'm having an issue.
What's the issue?
Oh, I don't know if it's just me, but I'm having an issue with the audio.
Okay. Oh. So, do you have a clue on what is a stochastic process?
Maybe the process that changes with time.
Yes, that is an example. You're right. You're right. Let's go back to the definition of the random phenomena. As I just wrote, the random phenomena is something that is telling me that there is, whatever will be the output, whatever different outcomes that we got, but there is some underlying patterns. Stochastic processes are those specific random phenomena that could be parameterized by just an index, t, for example. And that is your example. For example, it depends on time. And that's good. Okay. So stochastic process is a collection of random variables parameterized by an index t, whatever it be. And as your colleague suggested, could be, and it is often, the time. Okay. But that is not the only possibility that we got. Okay. So please distinguish between a random phenomena and the capability of your whatever model to capture, to represent those random phenomena, okay, through the underlying patterns. If there is just one underlying pattern, if we can parameterize all of those random variables as a result of whatever test that you were carrying out by just one index, then we are dealing. Now, let's have other question for you. When a stochastic process of the variable xt, for example, is stationary, another question for you. Do you have a clue?
When the probability function doesn't change over time?
Yes, that's the first part. That's good. That's the most important part if you want. So let me write that. So the first property is that there is no time dependencies, or better, there is no dependency from the parameter t. We are referring that to time, but that is not always said so. So a stochastic process is stationary if we have the probability density function, remember, okay, just could be expressed as in terms of the variable of the event x, okay, x. That also means that the average value and the variance, okay, are constant in time, or with respect to the parameter t, okay, to be more general. And that is the first one, the first property. The second property, B, is that if we consider the probability density function between two events, x1, t1, and x2, t2, and we compare this probability density function after, let's say, a variation of the parameter t, so x1, t1 plus t and x2 t2, sorry, no, yes, t2 plus t. And if we have this equal sign, that means that your probability density function depends on the difference between the two parameters t2 and t1, and not only of the absolute value of the values of t1 and t2 only. Okay, that is, let me write that, p depends on t2 negative t1 only, and not from t1 and t2. Okay, so that you can consider these probability density function between events. Okay, and if the phenomena, if your process is stationary, it doesn't matter when you start counting these variation, as long as the duration, as long as the t, capital T, is the same. Okay, so try to recap: a stochastic process of a phenomena that is parameterized by a parameter T, okay, is called to be stationary if your T is not important from the evaluation of probability density function, that is, the average and the variance are independent from time, and also should be satisfied that the probability between two events at two different times, okay, depends just on the distance between these two events and not on the value of the starting and ending time, okay, or parameters t1 and t2. Okay, please note that once your p of x is known, okay, then we are having a complete knowledge about uncertainty characteristics, or random variables. Is gained. Okay, so from the statistical point of view, your PDF is very, very important. Okay, because it's telling you what is the underlying pattern, what is the core of your whatever phenomenon that you are testing, that you are measuring, and that you are recording, for example, many, many outputs. Okay. Now, what time is it? Okay, 5 minutes break. Okay, and then we start with some other points on this. Okay, let's resume the class. And let's assume that we are down in the laboratory, okay? And we are characterizing one behavior, one physical behavior. Doesn't matter what behavior is, okay? But just let's assume that we are taking some measurements. And in order to do that, let's assume that we have n experiments. And for each experiment, we are taking that that behavior that is the one that we are having down, okay, that I just plot here. Okay, now as you can see, we have, for example, a parameter x1 that is measure, then the same parameter but with a different test has been measured again, so we are having x2 up to the nth evaluation of your whatever parameter. Okay, so what I can say is that we can have, for example, one reference time, okay, like this, okay, t, and corresponding to this reference time, we can consider all the outcomes from the n experiments like this, okay, and try to evaluate what is the average behavior. How can we do that? It is very easy. We can say that the average of the outcomes when evaluated at the parameter t, time t, for example, is given by this formula that you should know very well. Okay. Okay, where n is the number of experiment once again, and xn, x with the subscript n, correspond to the value of the nth experiment time t, referring to a specific parameter, specific physical value. For example, the acceleration in one specific point in your room floor, for example, as time passes by. Okay, so we are taking this experiment once, and then we come back tomorrow, we retake the experiment, then we come back after 1 month, and so far and so on. Okay, so that we have all these n experiments. This way of taking the average is called the ensemble average. Okay, and that is, okay, average of the ensemble. This way of having this average. Now, let's assume to have a lot of time available, a lot of resources available, so that we can have a number of experiments n that is very, very large. So if n, the number of experiments is going to infinity, okay, then it is possible to show that this limit for n that is going to infinity, that is the number of experiments taken, is very, very large, of this average of the ensemble is equal to the integral from all the domain, okay, of your x times the probability density function evaluated at the time t in the x. Okay, and this is the definition of the expected evaluator operator. is expected. So underline this. Expected value or expected Pareto or ensemble average. Okay. Once again, what is the expected value of whatever measured quantity? Is the average at a prescribed value of the parameter t, okay, of all the tests that have been recorded, that have been measured, okay, x1, x2, xn. Remember, xn is your nth test that is giving us the information of the evolution of your whatever random variable, okay, x in this case, okay. Now we can also think to consider just one test, okay, and take the time average, okay. So for example, let's focus on one of these tests, for example this. Let me focus on the nth test that we take. Okay. Then let's have this behavior. Well, instead of going in the vertical line, let's go in this horizontal line if you want. Okay. So let's evaluate the time average of the same physical quantity, okay, as your n, that is your time average associated to the nth experiment, okay, that is equal to 1 over capital T. I'm going to define that in a second. Then the summation from I to n of x n t I, for which t is equal to t evaluated at the nth sample time, negative the first one, and the ti are the time instants in which the function is known. Okay. Now, if n, this time instance, are going to be large number, okay, please remember n here is the time instance. Oh, sorry. So if n is going to be large, okay, that is your overall time is going to be large as well, okay, then the limit when n is going to be infinite of your 1 over t summation time from 1 to n x n time e could be reviewed as the limit by t that goes to infinity of 1 over t and it goes to 1 to t x n of time e, and we can prove that that is equal to the limit that goes for time that goes to infinity 1 over t integral from the beginning to the very end t of the x and t in dt. Okay, and that is your time average. Please remark that generally what we are having is the only limit number of experiments xn are available. Okay, we can't spend all our life in laboratory and taking the experiment, of course. Okay, and most of the time, that is what's happening, we have just one test available, just one experiment available. Okay. And thus, it is very important to have some tools to cope with these tests that are random, but there are some properties that we can use. For example, we can refer to stochastic process. Okay, so the question is now, how can we deal with just one test? When I'm referring to deal with, I'm just saying that how can we characterize these tests from just one measurement, for just one experiment, if we need to have a number of tests like this, okay, in order to represent what's happening to the overall ensemble. Okay, here comes the statistical property of ergodicity. Okay, so what we can say is that a stochastic process is ergodic if your time average is equal to the expectation value, okay, of your x of t. Okay, so your average in time is equal to the average of the ensemble. Okay, and that is for whatever xt, so whatever time average, and that is very, very, very important because ergodic processes are very useful for the evaluation of statistical properties. Okay. With that, just because go back to the laboratory, virtual laboratory, of course, as we considered before, if you would like to characterize whatever stochastic process, okay, we need to have a number of tests that is very, very high, okay? If that is true, then the expectation value, the operator E, could be defined in this way, okay, and therefore we could be very sure that your whatever stochastic variable is represented by the probability density function. But in order to do that, we have to have very high number of experiments, okay? But if your phenomena is ergodic, if your stochastic process is ergodic, better, then we can say that the average, okay, in the time domain is equal to the average of the ensemble, then we are free to choose whatever experiment, okay, in order to characterize your statistical property, sorry, of your whatever stochastic process. That is, instead of characterizing your, from the statistical point of view, your process going down this vertical direction, okay, we are going horizontally, okay? Just pick your process, just pick your experiment, and then you can have whatever parameter that you like from the statistical point of view. And that is a great saving in time and money, because what you need is just a very long, because we need a very long time series, but just one test, okay, carried out. Beware that this is true and only true if your stochastic process is ergodic, okay? Please note, just want to remark that stochastic processes are not generally ergodic, okay? That is, we can't confuse the time average with the ensemble average, okay? If you can't do that, then there is nothing we can do, okay? We have to take a lot of experiments, okay? Now, having said that, let's focus on, once we know that the process, that the random data that we got are not only stochastic, but also ergodic, they are stationary, remember, we are ergodicity, that is the other parameter, the other property that we are considering. Now, let's characterize, or let's introduce a way or measuring the distance from the statistical point of view of two outcomes, okay? In order to do that, let's consider this expectation value, E, remember the ensemble, the average of the ensemble. But now, when considering your whatever parameter, whatever random variable, okay, and the same random value, but this time shift by a quantity tau, okay? So we are evaluated what is the average, and therefore how two random processes are, let's say, the same or different. In this case, because we are having the random process that is count twice, we have x of t and x tau plus tau. So these two random processes are fictitiously two, there is just one. Okay, but however, let's evaluate this first. This expectation value is by definition what we call Rxx of tau, and this Rxx of tau is called the autocorrelation function. Okay. And this autocorrelation function is telling me how far or how close two events xt, okay, are when there is a time shift tau. We can prove two important properties of this autocorrelation function. The first one is the autocorrelation function at time shift tau equal to 0 is equal to the expected value of your x squared, and that is the ensemble mean square we can also prove that the autocorrelation function at the time shift tau, whatever, okay, is equal to Rx6 of negative tau. Okay, that is, your autocorrelation function is a symmetrical function with respect to the y-axis, okay, with respect to the time shift tau. Okay, let me call that time shift, right? And sorry, there is a third hypothesis, a third property. And this property refers to the fact that the maximum value of your autocorrelation function is at the time shift is equal to 0. Okay. That is a definition, okay, or how close or far are two events in your process, in your stochastic process. Now, if the process is also ergodic, so if is also ergodic, then we can mix and match, if you want, the time average and the ensemble average, okay? Therefore, what we can say is that the Rxx, that is the autocorrelation function that is dependent on the tau, that is the time shift, is also equal to the limit, the time goes to infinity, of your parameters, okay? That is 0 to tau xt plus the time shift tau in the tau. Okay. We can also try to see how close or far, doesn't matter, of course, are two different processes. Let me call that xt and yt. In this case, what we are having is that the cross correlation function is defined once again by introducing the ensemble average, okay, that is your rxy of the time shift tau, is by definition the ensemble average xt yt plus tau. And if there is the ergodic properties, then we can write that as limit of tau st, sorry, it goes to infinity, 1 over t, integral from 0 to the t, xt, yt plus tau, this. Okay, so these are two important considerations, two important properties, two important parameters from the statistical point of view that we need to consider. And these are the auto and cross correlation function. Okay, by definition, these auto and cross correlation functions are evaluated as the expected value of the product xt and y, that is your time shift. And what does this autocorrelation function, this correlation function mean? Are representative of what is the distance of these two events. Of course, when you are referring to the autocorrelation function, then this distance has an evident meaning, that is one event that is of the same nature as another event that is representative of X distribution. Then we can speak about this distance as the distance between two homogeneous events. When referring to two completely different function of processes, X and Y, could be, let's say, the vibration, the acceleration in a certain point, and let's say the number of flying vehicles, okay, then of course this distance has to be understood, has to be quantified in a different ways. But however, the cross correlation function in this case, yes, is telling you what is this difference. Another important thing is that although these definitions of the auto and cross correlation functions are referring to the expectation operator E, then if we are dealing with ergodic, stochastic and ergodic processes, then our work is very, very easy, because we can exchange the ensemble average with the time average. So we don't need to stay in the laboratory and taking a lot of tests so that we have a set of responses, for example. But what we have to do is just to consider one experiment, one test for a long time, of course, and then evaluate your auto and cross correlation function just by taking the time integral, as I wrote here, from the auto correlation function point of view and from the cross correlation function point of view. Just to give you an idea, let's consider, for example, a process that is characterized by a Dirac. Okay, so if your ergodic stochastic problem is white noise, okay, then, as I told you before, the autocorrelation function, okay, is sort of k times the Dirac. What does it mean there? Let's assume to have your whatever time responses, that is something like that, and then let's consider this once again, okay, but a time shift. Okay, so let's consider for example, the same function, but a time shift tau. So let's say, for example, this. Let's count on this. So let me move this in this way. So what we got is so this part, my intention, this part is this one has been shifted from the original position in time to a time plus tau. Okay, when you are correlating these two, okay, so what you have to do, time shifting for that, and then sum everything and take the average. Okay, that's what you have to do, and the result in terms of the autocorrelation okay, is just a Dirac of amplitude k. Why that? Simply because, sorry, also here I have to introduce tau. Okay, that means that because we are dealing with white noise, by definition, white noise, it is completely noise. It is a basic function. What we are having is that if we have these two functions, x and x plus tau, when tau is equal to 0, we are having that these two signals are the same. So we are having the maximum value of your correlation function. But as soon as we are shifting these two signals by a tau quantity, all these outcomes are completely uncorrelated one each other because of the additional noise, and therefore what we are having is that the correlation is 0. There is no correlation at all between that signal, and that's the reason why we are having always 0, but just tau equal to 1. We're referring to white noise. That is our ideal behavior. If we are having, for example, a more realistic behavior for which, for example, we are correlating the output acceleration in your floor, in a position whatever in your floor. Now you take the measurement for, let's say, 1 hour, and then you come back during the tomorrow, for example, we take that, then you can correlate this result, and as an actual behavior could be viewed as something which we are having by higher value, and then going down like that. Okay, and then we have a symmetric behavior over this. That means that as soon as we are increasing the time shift, the correlation between these two signals reduces. Okay, because we have something related when tau is very, very small. Okay, but as soon as the times tau start to be very far, very distant in time from the beginning, then the output acceleration, for example, in our analysis, could be something no more correlated. That's the reason why when we are increasing tau, we are having, let's say, 0 value in the autocorrelation. If, as a result of that, xt is not correlated with yt, then your cross correlation function is, of course, 0. And by the way, we are having null 0 average. I said that. Okay. When we are referring to the whatever cross correlation function, then we can't say anything else. Okay, we can't say anything because the behavior could be whatever. Okay. What happens in the frequency domain now? In the frequency domain, what we are having is that we have to refer to the power spectral density. Before talking about that, let me introduce a little bit how we can move from the time to frequency domain. So this last, let's say 10 minutes, let me talk about the Fourier series. This information should be known to you. Okay. And therefore, if we are having whatever function, now it's not related to what we discussed now. I'm just introducing the time to frequency transformation. Okay, so if we are considering a function t that is periodic function of period t, second properties, at least piecewise function continuous, and the third property is a limit function that is the integral, okay, of this function there exists its value, then we can say that your function t has a series expansion of this form. Ft equal to the expansion of n that goes from negative infinity to plus infinity of Cn times E J n omega 0 t is equal to 2 pi over t, and the coefficients Cn are 1 over t integral from negative half t to positive half t, or your ft times e to negative j and omega 0 t in the t. Okay, so as you can see, what we are saying is that your function could be represented as a series of harmonic functions, sinusoidal function in the complex domain. So let's see that in a complex domain. Okay, Cn, the coefficients are in general complex, complex value, generally. Okay, but if your function of t is a real one, okay, then your coefficients are so that the positive index coefficients are the complex and conjugate of the negative index coefficients. Here, these stars means complex and conjugate. Okay. Moreover, if the function not only is real, but also a even function, then your coefficients are all real. Okay. If we are having a lot of these terms, okay, then we can move to the Fourier integral. So prefer that previous we had the Fourier series, now we have the Fourier integral. What we are requiring now is simply a non-periodic function, or if you want, the period is going to be infinite. That is just a limit function that is satisfying this condition. This limit function. Oops. Okay, then this function can be expressed as a limit of a periodic function of period t. Okay, as t goes to infinity. Okay, that is, your ft could be written as the integral from negative infinity to infinity to its frequency domain representation, capital F, e j omega t in the omega, or vice versa, your frequency domain representation of your whatever function, capital F, is the integral from negative infinity to infinity of your ft e to j omega t in the t. Okay, so these two expressions are, one is the tool to go from time to frequency domain, the other one is the reverse, and these are very, very close, if you want, to the Fourier series, but now we are talking about different things. In the first case, we are referring to the chance of expressing one function is satisfying some specific condition as a combination of harmonic, of periodic, or sinusoidal waves, sinusoidal and cosinusoidal waves, whereas the Fourier integral is representing your function as the Fourier transform, that is, as the Fourier representation of the frequency domain representation better of your starting point. So that is a transformation itself. Okay, so time is over. Let's keep going tomorrow on these topics, and then we have some other interesting things to discuss about. So that's it for today. Do you have any question? Okay, so if there are no questions, thank you so much. See you tomorrow, same time. Bye bye.
Arrivederci.
Arrivederci.